Our next speaker is Alhussein Fawzi, who is a research scientist with Google DeepMind. He did his PhD at École Polytechnique at Lausanne in image classification. And he's going to continue the deep learning theme now to tell us about how we actually do some mathematics and discover proofs using deep learning. Thank you.
Thanks a lot for the invitation. Thanks a lot for having me. Yes, so I'm Hussein. I'm a research scientist at DeepMind, and I've been mostly working on the robustness of neural networks. How can we show that, how can we improve the robustness of neural networks? And recently, I've been discovering a new topic, which I think is very exciting. I'll try to tell you why is it exciting, which is basically how can we use machine learning in order to prove statements and do mathematics, basically. This is joint work with Mateusz, who's from DeepMind, Hamza, who's a professor here, Omar, who is a professor at UNSW. Okay, so I guess you all know that in the recent years we have seen huge improvements in many tasks in machine learning, whether that's image classification, captioning, speech recognition, image generation, and so on. So mostly tasks that involve some perceptual data, like speech, images, and so on. But very recently, we also have achieved huge improvements in games, like, for example, playing the game of Go, and very recently StarCraft, and so on. Most of the advances that we have seen are due to the fact that we're using very big models, deep neural networks, which we just had a great talk on. So the models get really bigger and bigger, and the improvements gets better and better for all these tasks in the last few years. Despite this, like most of the networks that we're actually using, and in most of the tasks, we actually don't have any proof or certificate, basically, about the outputs that the network basically spits out. So in other words, if I basically want to classify that an image, let's say an image of a rabbit or something like that, then I basically get as an output that this image is that of a rabbit. Okay, so I don't have any sort of proof or anything like that this is indeed a rabbit, right? So it doesn't give you something like this is okay. It doesn't basically tell you that this is an image of a rabbit because you know, this is an animal with 2 eyes, long ears, fluffy, and so on and so forth. So you just have to trust the network. Okay, and this is really problematic from like a safety perspective. Like if we want to implement these neural networks in real-world applications, we really want to have some sort of proof or certificate that the outputs that we're getting from the networks are correct. And by proof or certificate, I really mean that someone expert in rabbits should be able to basically certify that this proof is correct, right, in this case here. So yeah, so we just have to trust the network. I should mention that in the last few years, there's been a huge amount of work on trying to make neural networks more interpretable by basically getting some sort of clues about why the network outputs something. Okay, like for example, it would tell you some reasons why, but it would never be a sort of like a complete proof or anything like that, obviously. And even if it actually was able to give you some sort of proof, the proof would actually be wrong in the sense that we actually know that neural networks latch onto like a very simple patterns rather than actually doing reasoning. Okay, so it doesn't really classify this image being to be a rabbit because of like some sort of reasoning of the image or something like that, but because it has like identified very simple patterns that us humans consider as actually completely meaningless. And the evidence behind this, what I just said, is the existence of adversarial perturbations. And here, for example, the existence of universal adversarial perturbations. So you might know already that if you have basically a neural network, a state-of-the-art neural network, you can add a very simple pattern, just a single pattern, to the different images and have basically all the images being misclassified by this deep neural network, despite the perturbed images being very close visually to the original images. Okay? So this simple pattern here, kind of like a magical pattern, you can add this pattern to all the different images, okay? and basically cause the classifier to completely misclassify. So for example, this image of a joystick here would become a chihuahua, this image of a flagpole would become a Labrador, and so on and so forth, just by adding this very simple pattern here. And these are the perturbed images, these are the original images, right? So for us as humans, we don't see any difference between the left-hand images and the right-hand images, but the network sees something completely different. And this really tells us a lot about the fact that the networks really don't do like the reasoning that we're expecting it to do, okay? So what I'm really after here in this talk today is really to try to identify whether networks can do the reasoning that like proper reasoning. So what we're after today is really having verifiable proofs of the network decisions. And if we want to basically understand whether networks really can do reasoning, we have to work in a domain that is the really pinnacle of reasoning, which is mathematics. Okay, so so what we're after here today is, we want to prove or disprove a statement starting from some axiom and using some well-defined inference rules. So we would start with some axioms, and then from the starting axioms we want to derive lemmas, and then from the lemmas other lemmas, and so on till we find basically the proof of our final theorem, which is our objective. Okay. And the very important thing here is that the correctness of a proof can actually be verified mechanically. So I can basically, if I have the knowledge in mathematics, then I can do it myself, or I can even give it to a computer, and this can be verified mechanically. So I don't have to trust the network. I don't have to trust that the network just told me that this theorem is correct or this theorem is incorrect. Okay. And obviously the hard part is basically coming up with the proof. So coming up with a path from the axioms to the theorem. Okay, and this is where we're going to use basically machine learning. So let's take this example. So I want to prove, for example, or disprove Cauchy-Schwarz inequality. Okay, so we're going to give this to a neural network, and then the neural network is not going to only to tell me that this is true, but it's also going to give me some sort of proof. Okay. And then I can basically verify this automatically. So obviously that's the optimal scheme or the ideal scheme that we want to long to in the next few years in deep learning. Okay, so I don't think I need to convince this crowd, but you might think that this is maybe of an academic exercise. Why do you want to do like machine learning? Why do you want machine learning to do mathematics? There is actually a very large number of applications in order that would be in which machine learning can help doing proofs. In particular, in safety critical applications where we want to do some sort of program verification or verification of security protocols and so on. This can be extremely helpful in order to find proofs. So I don't need to I guess most of you are aware about the fact that program verification is something extremely important from a safety critical perspective. Like for example, the crash of Ariane 5 is due to the fact that there is a software bug, basically a bug of conversion from one type to another one, which led to a crash of Ariane 5, basically. So it was about the horizontal velocity of the rocket, which was wrongly converted from a type to another type, and basically led to a complete crash of the aircraft, and hundreds of millions of dollars were lost. And so we really want to develop these proof systems in order to improve the way we can do program verification, as well as the verification in control theory, for example. Okay, so so we're going to work with polynomials. One of the reasons why we want to work with polynomials is basically that they're very general, in the sense that like any continuous function can be uniformly approximated with a polynomial function, but also it has a lot of applications in the areas in which I'm interested in, for example, control theory, robotics, program verification, and so on. So many of these problems of verification can actually be cast as a polynomial system of equations, or proving some sort of polynomial inequality. Okay. So let's see how we can actually, for example, cast a problem, a geometric problem that seemingly doesn't have any relation with polynomials in a polynomial form. So let's say, for example, we take Ono's inequality, which basically tells you that let ABC form an acute triangle, and then we want to prove an inequality on the area and the length of the triangle. So ABC is the length is basically of the triangle of the of the edges of the triangle, and then so this is basically relating the area with ABC. So what you can do is basically to translate the geometric objects into polynomials. Like for example, you might want to say that an acute you can write the constraint that you have an acute triangle with a system of polynomial equations, and you can write the area here in function of the length of the triangle, and you end up basically with a polynomial system of equations. So this is not the only example, obviously, where you can write a geometry problem using a polynomial system of equations. Actually, if you embed it in a Cartesian space, then actually most geometric problems you can write them as a polynomial system of equations. Another example where, that is going to be interesting for us today is basically formulating combinatorial problems with polynomials. Let's take, for example, the problem of a stable set, the maximal stable set, or the independent set. It's equivalent. Let's say you have a graph, okay, and you basically define the stable set of the graph to be a subset of vertices such that for every 2 vertices in S, there is no edge connecting the two, okay? So the stable set problem basically corresponds to finding the largest stable set in the graph. So for example, let's consider the pentagon graph here, okay? So the largest stable set in this graph is of size 2, okay? Because if you basically, like, let's say you pick this node and you pick this node, if you pick a third node, then you're basically going to violate the constraint that there must not be any edge between 2 vertices in the set that you have chosen, okay? So let's say you pick this one, for example, then there is an edge here, okay? And if you have a complete graph, then the maximal stable set is of size 1, okay? Because obviously if you choose any other edge, then any other node, then there is going to be an edge. Okay, so this really doesn't seem like anything related to polynomials, but actually you can write this problem as a polynomial optimization problem. So we'll basically have a variable x which lives in Rn, where n is the number of nodes, okay? And then we want to maximize basically sum of xi. Okay, so xi is going to be either 0 or 1. So 1 if we're going to take this node in our set, and 0 otherwise. We're going to constrain basically xi xj is equal to 0 for all ij edge in a graph. Okay, so that we don't have basically two nodes that are connected by an edge in our set. And we're also going to say that, okay, xi has to be either 0 or 1. So equivalently, xi squared is equal to xi. Okay? And then like what we'll be interested in is proving that there is no stable set that has cardinality larger than some gamma. Okay? So there are 2 sides to this. Like either we basically have a feasible solution for which it would give you an upper bound, or we basically prove a certificate that there is no stable set larger than something for which it would give you a lower bound. So we're interested in basically providing a lower bound. Okay? Any questions? Okay. Okay. So let's try to write down the framework like more generally. So what we're interested in is proving a polynomial inequality. P of x is non-negative for all x that satisfies some axioms. G1 of x is non-negative and Gk of x is non-negative. Okay. And obviously, if we want to prove this, the fact that the polynomial is non-negative for all these axioms, then we need to have some rules to go from one step to the next step, right? So basically deriving lemmas one step at a time. So the way we do this is by defining inference rules, which basically are ways to maintain the positivity of a polynomial. So basically, you would start with a polynomial that is non-negative, and then by applying an inference rule, you'll get another polynomial that is non-negative. Okay? So the inference rules that we're considering here is if you have a polynomial that is non-negative and you multiply it by one of the axioms that is also non-negative, then you get a new polynomial, GIH, that is non-negative. Okay? So that's our first inference rule. The second inference rule we have is that if you have a bunch of polynomials that are all non-negative, and you do a non-negative linear combination of these polynomials, then you get something that is, again, non-negative. Okay? So that's the two inference rules we have here. And then my goal is basically to prove that P is non-negative. And the way I will do this is basically to try to find a composition of inference rules starting from the axioms in order to arrive to P. Okay, so it's basically a path finding problem starting from G1 to GK, which are axioms. I want to basically arrive to P. Okay. So let's try to see an example of a proof. So let's take the same problem as I considered before, which is the stable set problem. Okay, so I just rewrote here the stable set problem for the complete graph, and then I want to prove that that the stable set for a complete graph is 1. The maximal stable set of the complete graph is 1. So how do I go about proving this? Basically, so I would start with my axiom that 1 minus x1 is non-negative, okay, which is one of the GKs that I just listed in the previous slide, and then I'm going to multiply this by 1 minus x2. Okay. I'm going to get this polynomial here, which I'm going to simplify using x1, x2 is equal to 0. So I'm going to get 1 minus x1 minus x2 is non-negative. And then I'm going to multiply again by 1 minus x3, and so on and so forth, till I basically get the final polynomial that I care about, which is 1 minus sum of xi's. So once I prove that 1 minus sum of xi's is basically non-negative, it basically tells you that the stable set for the complete graph is 1. The maximal stable set for the complete graph is 1. Now, note that in this case, the intermediate polynomials in my proof did not exceed a degree of 1. They're always degree at 2 at most. Okay, so they never go beyond degree 2. Okay, so this is important because the degree of intermediate polynomials kind of characterizes how difficult is how complicated is your proof, and we'll come to this in a second. Any question about this proof, about this slide? Yeah. Okay, so as I just highlighted, it's really a problem of starting from some axioms and basically searching over the set of lemmas and arriving to the polynomial that I care about eventually. So in order to do this, what we're using is basically a reinforcement learning framework where you have an agent, okay, that interacts with an environment. The agent is basically the prover that is at each step is going to choose an action, and the action is going to be a polynomial that is non-negative, okay? And the environment is basically going to give you back a reward and an updated state. Okay, so you're basically having an interaction between an agent which chooses an action, and then at each step the environment is going to reply back to you with a state and a reward, and the reward is basically going to tell you whether you achieved your result or no. So let's say, for example, you can think of a reward which is 0 as long as I did not prove that my polynomial is non-negative, and 1 if you did prove that your polynomial is non-negative. Okay, and our goal is basically to maximize the sum of future rewards. Okay. So I just don't want to maximize the reward at the current stage. I really want to maximize in the hindsight, the full reward till the end of my episode, basically. Okay. So what we'll be using here is a reinforcement learning algorithm called Q-learning, where the main object in Q-learning is basically what we call the state action value function, which is basically what we denote here as Q, which is basically going to tell you if I start from a state S and I take my action A, how good is this action starting from S? Okay, so basically the higher Q is, the more interesting taking the action A at the current state S is. Okay, so we're going to try to learn this Q value function from the data, as we'll see. And basically at each step we're going to try to choose the action that leads to the maximal Q value. Okay, is that clear? Yeah. Okay, so I'm not going to go into detail into how you can actually learn this Q, but it basically relies on Bellman optimality equations, which is basically a kind of like a recurrence relation between the Q values at different states. Okay, and then, as I said, if you learn the q value, then a q value function, then you can basically extract from it a policy by taking the action that leads to the maximal value at each state. Okay. Okay. Now the problem with this is that if we want to apply this q learning function, q learning kind of like algorithm out of the box right away, it's not going to scale to our problem at all. Okay. In other words, in our problem, we cannot actually list all the different states. There is an enormous number of states, basically. So the state is basically the number of possible lemmas that you have derived. Okay, so and the number of possible polynomials that you have derived so far, which is really very, very large in our case, and actually infinite in our case, because the number of positive polynomials that you can derive at each step is actually infinite, because you have, you know, like the coefficient in front of each polynomial. Remember, we have two inference rules, one which is multiplication, the other one is non-negative linear combinations, right? So you can do non-negative linear combinations, an infinite possible number of non-negative linear combinations. So similarly, in computer Go, we had a number of states which is actually very, very large. So if we are to kind of like solve this kind of problem, we have to use some sort of approximation. And the traditional way of doing this is basically to use a neural network to approximate the q-value function. Okay? So we don't basically consider the tabular view where we're going to basically fill all the q-value functions for all states and actions, but rather we're going to learn a global function, a neural network, which is going to basically tell us what is how interesting is to take the action A at starting from state S, okay, for the interesting states that we care about, okay, not all the different states, because we don't care about all the different states eventually, okay. So the idea is to replace this tabular view with basically a neural network that takes as input a state and an action, and basically get outputs basically how interesting the action is from state S. That's going to be our neural network. And by the way, this is the approach called DQN, deep pure networks, that was very successful in playing Atari games back in 2013, and really created a breakthrough in reinforcement learning. Okay, so let's go back to our problem. How are we going to apply basically deep Q networks or Q learning in our problem? So remember that our agent is our prover, and in our case, the state is basically characterized by several things. So first of all, it's going to be characterized by a memory, which is called here M0 for the memory at step 0, which is going to be all the polynomials that I have so far proven to be non-negative. Okay, so let's say I've proven, like I start with the axioms, basically x1, 1 minus x1, x2, and 1 minus x2. All these things I know are non-negative. Okay, now the next action, so I'm going to choose an action basically, and the action that I'm going to choose will basically consider one of the elements in the memory that I have and apply an inference rule to it. Okay, so let's say, for example, I pick 1 minus x2, and I multiply by 1 minus x1, and I multiply by 1 minus x2. So this gives me basically 1 minus x1 minus x2 if I do the reductions, which I'm going to add to the memory. Okay, and then from this, I'm going to update my state, which is basically my memory, and give you a reward. Okay, so this is the memory part of the state, but there is also the equalities. Okay, which is basically going to be all the equalities that I have. Xi xj is equal to 0, for example. This is also part of my state, and f is basically going to be my polynomial that I want to prove eventually. Okay, to be non-negative or to maximize. So so basically we do this on and on again. So the prover basically at the next step is going to choose again another element from the memory, apply one of the inference rules, add it to the elements of the memory, and so on and so forth. Okay. So the equalities and the function we want to prove are static, so they don't change through time. It's only the memory that changes through time in this case here. Okay. So now, as I said, we use DQN or like Q learning to train the prover. If we basically apply it directly, we won't get very good results. Actually, we won't get any results at all. We really have to design the rewards and put some symmetries in the network in order to make this work. So we're working with like mathematics, and in mathematics there is a huge number of symmetries. The networks have really hard time understanding the symmetries in the problem, and so we have to incorporate these in the Q network. The other thing is that the rewards are extremely sparse. If I just give a reward at the end of the proof, basically, if 1 if I prove it correctly and 0 otherwise, this is not going to lead to good learning at all, because it's very hard actually to know after 1,000 steps, for example, I give you 1, you don't know exactly whether this 1 corresponds to the step you've taken in step 57 or the step taken of 152 and so on. So it's extremely hard to learn in sparse reward settings. So what we're going to do here is we're going to densify the rewards. So we're going to give you a reward at each, like, or at every time you do some sort of interesting move, and also incorporate symmetries in order to get good learning behavior. Okay, so how do we define the reward signal? So as I said, the easiest option would be to define just a 1 reward at the end and 0 otherwise. Now this has 2 problems. I discussed the sparsity problem. It has another problem, which is that you need supervision, right? So you really need to have some sort of oracle that tells you what is the optimal bound you have for each problem you have in your training set. So for example, in our stable set problem, you need to build graphs as well as their optimal, the maximal stable set for this given graph, okay? Because you basically give a positive reward each time this optimal value is reached and 0 otherwise, right? So in our case, what we have is instead dense and unsupervised reward, and the idea is to give reward whenever the bound that you derive from the lemmas improve, okay? So at each step of the reinforcement learning, so remember that the reinforcement learning is all about this loop, this step interaction between agent and environment. So at each step, what we can do is basically to solve a linear program and determine what is the best bound that I can derive from the elements that I have in my memory. Okay, so I can basically, so f is the thing that I'm trying to maximize here, and then I'll try to, gamma here is basically the bound that I'm trying to see. What is the best bound that I'm trying to minimize? So I'm trying to minimize the gamma. Subject to gamma t minus f here is basically non-negative. So I'm trying to find the non-negative linear combinations of the elements in the memory that I have that basically results in gamma t minus f being non-negative. Okay, so if I have basically that gamma t minus f is non-negative, then I have proven a bound on f, which is gamma t. Okay, so I'm trying to find the best linear combinations of the elements in the memory that I have that gives me the best bound. Okay, so this really is something like very useful in order to shape the rewards. That's what we call reward shaping. Basically makes the rewards much more continuous. And once we solve this linear program here, what we can do is that we define the reward as a difference between the gamma that you get at the current step and the gamma that you get at the previous step. Okay, so that's basically the improvement in the bound that you get at each step. Okay, so if I've chosen an action that is interesting, then basically the RT is going to be non-negative, and therefore I'm going to give a reward for this particular action, and the learning would be much faster in the sense that it would know that the action that I've just chosen is interesting and not maybe an action that I've chosen 100 steps ago. The other thing that I mentioned is symmetries. You need to incorporate these sort of symmetries. So you're working basically with polynomials and sets of polynomials. So the first symmetry we need to incorporate is basically the fact that we're working with sets of polynomials. So if you basically shuffle around all the lemmas that you have, you need to have exactly the same q-value function. So we put this explicitly in the architecture. And the other invariance you need to put is basically that if you relabel all the variables in your polynomials, then you basically need to get the same q-value function exactly. So let's say you have a problem where x1s and x2s and x3s are involved. If you shuffle around x1 and x2 and x2 and x3 and so on, it basically it's exactly the same problem where you just rename the variables accordingly. So So you need to basically incorporate this. I won't go into detail how do you incorporate this, but if you're familiar, for example, with graph neural networks and so on, these are very good kind of inductive biases to really incorporate these symmetries here. How much time do I have? 5 minutes, okay. I'll just very quickly mention like a baseline that is really used in algebraic geometry here, which is what we call the static proofs. So the static proofs try to bypass basically the need for a search algorithm. Obviously, like the hardest part here is to have a search algorithm. So what people do instead of basically considering this search algorithm is basically to say, okay, I'm going to unroll my inference rules for a fixed number of times. Okay, so let's say for L times here, okay, which will basically so if you unroll for, let's say, 1 or 2 or 3 times, for example, you'll always get functions of this form here. Okay, and then once you get functions of a fixed form here, what you're going to do is you're going to search for a proof in this restricted set by solving a linear program, basically. So the problem of searching for a proof amounts to solving a sequence of linear programs starting from the first level of the hierarchy corresponding to L is equal to 1, and then solving a linear program for the second level of the hierarchy if you didn't find a proof in the first level of the hierarchy, and so on and so forth. So it's really about unrolling for a fixed number of times and then solving, and then unrolling for 2 times and then solving, and so on and so forth. But the problem with this approach obviously is that the proofs might actually be very, very long, in the sense that the level of the hierarchy you need to go to if you want to prove that some polynomial is non-negative is actually can be much larger than the degree of the polynomial that you're trying to prove. Okay, so I'm going to go very quickly into the kind of results that we can have with this approach. So we trained on the stable set problem. And we basically then tested on other graphs. Okay, so we trained on random graphs of size 25 nodes, and then we tested on graphs that we care about, like that have symmetries and so on. So this is, for example, the proof that you get as an output that the complete graph of size 7 here has a maximal stable set of 1. So that's the output basically of the neural network. So it actually very much corresponds to the proof that I showed you in the previous slide, in the sense that it really builds sequentially this proof that the fact that sum of xi is less than 1 by basically proving that first 1 minus x3 minus x7 is less than 1, and then 1 minus x3 minus x7 minus x6 is less than 1, and so on, by multiplying the previous steps by a new polynomial. Okay. So it has this very much sequential structure to it that I showed before. But then you can also prove things like, for example, the cycle graph, which is known to be hard, and you can basically get the optimal bound here, 3. This is a random graph, and then you can compare basically this dynamic approach that I just talked about with the static approach, which is basically used in this field, which corresponds to unrolling the inference rules for a fixed number of times, and you can show basically a huge improvements in terms of the size of the linear program that you need to solve in order to get the proof. So you can imagine that the static approach is really like solving huge linear programs, because like if you unroll like the size of the space is basically exponential with respect to the number of times you need to unroll basically the inference rules, obviously. So this can be really, really large, and so this dynamic approach kind of like gives you a way to smartly search in this tree that I'm talking about. So let me know if you have any questions. Most of these results are in our NeurIPS paper, which is going to appear next week or so. I mean, NeurIPS is maybe in 2 weeks or so. So with that, I would like to conclude, and maybe just a final slide about like the things that I've learned by doing this project, basically about the difficulty of basically proving like mathematical proving with machine learning. I think I've identified a few challenges basically that one needs to really address if we are to kind of like make this scale up to very large instances. So first of all, there is the data generation challenge, which is the fact that we don't have a lot of labeled data. In other words, we don't have a lot of theorems that come with proofs. So we really need to be able to generate good training data that is interesting for us. Like, it's not really clear how you can generate theorems that are interesting for humans, right? So we can generate many training data, but like the theorems that you would generate are probably not very useful to humans. So how do you generate these kind of data is something very, very important, like a challenge that is very important, I think. Another thing I touched upon is the fact that the rewards are extremely sparse in this area. So you really need to find a good way to shape the rewards. You have a lot of symmetries involved in mathematics, so you really need to build these in the network. Trying to say that the network is going to learn them by itself from the training data is not going to happen. At least from my experience, is like it needs a lot of training data in order to understand these symmetries. So it's much better to build them in the architecture. And finally, we have very, very large action spaces. At each step, we have a huge number of lemmas that we can choose from. How do you, you cannot basically enumerate all of these. So finding good ways basically to leverage or to deal with large action spaces is definitely a challenge, I think, in this area. Thank you.
Thank you. So we do have a few minutes for any questions. Yes. Sorry.
Could you say a word about the computational cost
Of training or of testing?
of training?
Of training, okay.
So this is really impressive. The example you showed was relatively small one.
Yes.
Scale.
Yes.
What's the computational cost?
So currently we are only training on one GPU, which is not, I'm not really using the big computational power of DeepMind currently, but I'm trying to basically scale this up. The number of problems that the size of the training data is around of the order of hundreds of thousands, so it's not humongous. But I would expect that if we scale this up to thousands of variables, like polynomials of thousands of variables, then I think it would probably scale to tens of millions or hundreds of millions of training data. The problem with this approach is that we don't have any good way currently of dealing with the very large action spaces. So currently the number of actions scales quadratically with the number of elements I have in my memory, which is really not something that we want. So we're currently working on making this linear instead of quadratic. Yeah. So.
Showing this way that inequality is sharp?
Can we show that inequality is sharp? Yeah. So this gives you only a lower bound. It doesn't give you an upper bound. If you get a feasible solution, then you would get the sharpness. But this doesn't give you currently any feasible solution. We're really looking at getting certificates rather than getting feasible solutions. So do you mean that the proof might not be correct? We don't need to explore the entire space. I mean, we know that the proof that we get at the end is correct in the sense that it follows the inference rules, which we know are correct. And I'm not sure I get the yeah. Yes. Yes. Yeah, if we choose, yeah, actually in many cases here what we get is like intermediate steps that are completely useless, but that's fine. Like as long as we get a valid proof at the end, that's fine. Currently, it wouldn't tell you that this is not correct. I mean, so actually what we're doing is that we're trying to, yeah, we could, yeah. But actually what we're trying to do here is just to maximize a function. We're actually not giving it the bound. So we're not giving it like, an inequality of the sort of like p of x is less than 3 or something. We're just giving it p of x, okay? And then we basically try to maximize this p of x, okay? So in that sense, there is always a bound, at least for the functions that we're working with. So in that sense, there is no counterexample. There is no thing that is not true, basically.
Okay, thank you very much.
Thank you.